Hi, my name is Kevin Waldeck. I'm the CTO of High Mobility, and in this clip I will give you the status of the Cloud and Connected Services project. We'll walk you through just briefly first the charter for those of you who are not too familiar with the project so far. Then we'll have a look at the work we've been doing this year, which has been focusing a lot on a communication framework involving both in-vehicle components, cloud components, and third-party components. We'll also have a brief look into the relevant standards we have investigated and also in some cases incorporated into the communication framework. And lastly, about the CVII, Common Vehicle Interface Initiative, which is new, and also shortly how it relates to the CCS, so the Cloud and Connected Services project. Well, the project charter, what we aim to do in this project when we started out beginning of last year is to kind of realize that, of course the connectivity of vehicles is long here, but also then now how to enable any type of new services to simply be built, because there are a lot of different players who are in this kind of new mobility field, working on APIs, working on vehicle generated data. And in this project we aim to kind of look at what's out there, identify the different actors and also the different needs, and then kind of translate that into an architecture for the vehicle, and what are the components that are necessary for anyone who wants to enable data sharing from the vehicles or from the cloud, and on the other hand, what's really necessary to access this. And for that, we have this year been working on a communication framework. So as in the first step of the project, we were focusing on analyzing existing documents and standards and frameworks that are out there, and also comparing different data models and so on. We have now been active working kind of creating an architecture of what is the kind of communication framework from start to finish or end to end. We've also been working on a proof of concept implementation on this. So there's two sides. Of course, the proof of concept implementation is something to demonstrate how this works, but there are some other considerations that have to be done in a production environment. But we have had both of these things in mind, and we have been designing a framework that is general enough to kind of identify what are the basic needs and what are also the open standards or open ways of achieving this, and what are popular methods or libraries to do it. But then also from a POC perspective, how can we implement this in a relatively short time span to demonstrate it? If we start from the bottom right, we can see the vehicle. So here's where the data is being generated and captured within the vehicle. So to start off with, we decided in the project on VSS, so the vehicle signal specification, as the data model, because anytime if the data is generated from within the vehicle and then transmitted to the cloud and made available for third-party services, obviously it's very beneficial to use the same data model. So the data can be generated in this framework through already from an ECU side or from the very beginning in VSS data model, but it can also be using any type of proprietary or protocols on the CAN bus. So we have kind of considered this type of translation need in the vehicle, but in the end, when the vehicle states or data is being stored within the vehicle, it is always stored in VSS, in the VSS format. And then there's a data server, so it's possible for the cloud to basically connect to the vehicle to fetch the latest data, or possibly also in the future store data or cache data on the vehicle, and then access that into the cloud. So there's a transmission either over WebSockets or HTTPS to the cloud. And there we have a database where all of the data generated from this particular vehicle or maybe a fleet of vehicles is stored, and also that in VSS2 format. And then that data has to be made available, and different mechanisms have to be implemented for this. One is the resource management itself, so the data resources are made available, but also how is access managed, how is identity managed, what's necessary for consent, for that data sharing to further third parties. So we've been looking at all of these different components, and I'll give you the status of each one of them as we go forward. So in-vehicle components. So first off, the in-vehicle storage. To the top on the right hand side, we also have a small box highlighting which part of the framework we're addressing in a given moment. So to summarize, in this proof of concept, we use SQLite as the database. The implementation is done in Go. The source is also linked here, so you can see it on GitHub. And for the POC or proof of concept, this implementation is done. And what it does is that the state storage has two interfaces. One that is the input that comes from the data feeder, so any data that is generated by the vehicle, and then we have the output to the data server. And then the database itself is using SQLite as mentioned, but the manager implementation is done in Go, and the manager essentially configures the database, sets it up in the beginning, but then when the data is being accessed from the state storage in this POC, it's done directly over SQL. And in the code repository itself, we have the documentation how this interface looks like. It's also mentioned that the Gen 2, so this is the W3C second generation vehicle specification implementation that has been used, and we will have a look at that in the next steps, how that works. From the in-vehicle data feeder, so where the data comes from, we have been evaluating different simulators. So we have a simulator from LG, we have OpenDS, also GENIVI vehicle simulator from several years ago, and how they could be used. Essentially, in a POC, of course, we need some way of generating data that is then fed into the state storage so that it can further be transmitted to the cloud. Also, in the current work in progress, we are looking to reuse some of the backend or cloud work that will come to where we do store data, and actually using live vehicle data that has been stored in the VSS data format, and using that as an output, so we can essentially run historically recorded vehicle trip, and then from that we feed these events that have been captured in real life into the state storage, and that way it goes up again to the cloud and can be transmitted to third parties. So we have been doing the simulation of data capture, and this is also how we have implemented current POC of the data feeder, that we have actual historical data that is then fed from a database into the state storage within the vehicle. And for the data server, as mentioned, we're using the second generation protocol from W3C. And what it does, it supports both HTTPS and WebSocket connections from the cloud. Whenever a request comes in, it fetches the value from the state storage through SQL. Currently, just in the POC, if there's no value available, some dummy data is returned. So whenever the OEM cloud or connects to it, there's always some data that can be retrieved to have something up and running. And for the next steps, we are looking at different ways of improving this. Of course, error handling, so we don't return dummy data, but we can have proper handling of that, and also subscription. So currently, there is a request coming in from the cloud, OEM cloud, which is the client, that asks for a specific VSS signal, and that is returned. So the current state of that, or current value of that signal, is being returned. But it can also be, of course, beneficial to subscribe to different signals, and this is already supported in the Gen 2 protocol, but it hasn't been implemented in this project yet. The data server is also implemented in Go. The link is available for GitHub, where we have more documentation about this specific implementation. And in the kind of proof of concept implementation, it's already connected to both the state storage, so it can be used to retrieve data. One thing we kind of identified within this project was the need for a some sort of data package. And this is a data package that can encapsulate more than just one signal value whenever something is being transmitted from the vehicle to the cloud. So we can imagine that there's a need to send a time series of signals, so how the speed or location changes over a certain time point. Also different mixed signals. So if we are, so to speak, recording 10 seconds of vehicle data for 2 or 3 different signals, we would like to send that data package to the cloud. And also some other things like geolocation tagged signals. So if we are getting the speed or some other data, that we have both the timestamp and the geolocation connected to each of them, and that should be then transmitted in one data package, not individually. And we've also been considering job IDs. So in some cases, it does make sense that the cloud actually directs the vehicle to capture certain data, so not that all data is captured all the time, which would be not really a feasible implementation because the vehicle generates so much data. But you can have different jobs, and then in each data package you can refer to, okay, this data package was collected in the course of this job. Currently we're kind of been defining this type of protocol or how it can be used. There's no implementation yet, and this is something we will also discuss in this project workshop during the summit. But in essence, also there's no support today to transmit such a data package using the data server and the W3C Gen 2 protocol. So that's also something we need to look at. But of course, the data package protocol is not meant to be something, let's say, something new that has to be implemented by other projects. It's rather like a look at, okay, here's what we need. Here's what we see could be necessary, and then the implementation, or it could be included in any protocol that deals with these type of things. So the status is bottom right. You can see it's work in progress, so it's nothing finalized, but it's really something we've been kind of defining. And if you look at the Confluence link attached to the slide, you can see how long the specification has come today, and you can also share your comments. So that's for the in-vehicle components. Next, for the OEM cloud. So far we have had the data generated in the vehicle in a simulated environment for the POC fed into the state storage, and then made available to the cloud from the data server. And to access that data, we implemented the data client. It's of course using the Gen 2 protocol as well. It's written in Go, this component too. We have the link to GitHub, and it's also completed for the POC. It fetches the data currently on a periodical basis. So every X seconds, the latest value of certain signals is fetched. And when it is retrieved, then it's also stored into the database in the cloud. The cloud database is in the POC also written in SQLite, and we have a manager that is written in Go. It's a relational database schema that we have been also proposing in this project. It's how you can simply design the schema using the VSS data model. So it's very straightforward to save data from many vehicles, so many VINs, into the database, and also considering the time series that data is being transmitted often, also the different signals that can be processed. So we have linked here a proposal for how that can be done, and that's also what has been implemented in the POC. There's 2 ways of interfacing this database. One is directly over SQL, and obviously if you know SQL or can work with it, then any type of queries can be done, and also any type of data can be stored in any way depending on how the data comes in, how many vehicles it is. But this Go implementation also has a REST interface, which is just using that translates VSS2 paths into internal destinations, so internal tables and so on. So of course, if you have VSS knowledge, then it's very simple to use the REST interface of this database, because you can just use it, you can store data into it, you can also retrieve data from it. You don't have to know about the internal schema of the database. So the SQL version is really for the more advanced use cases when those are needed. Also mentioning here the Open Vehicle Dataset, so OVDS. That has also something that kicked off a discussion within the project, that this could be used for an open dataset that is stored in such a format as the proposed database schema, VSS schema. So that's of course one kind of use case you can have for it, for this type of VSS database that is being designed here. Now to the right, you can see the kind of focus goes more to the other side of the cloud and how to make that data available for services. So how can third parties access this data that's stored in the database and be used? So for the API interface, we have for the POC we have chosen GraphQL. Of course, it could be a REST API, it could be a socket API, it can be implemented in many different ways, and that we've also highlighted that in the communication framework. But for the POC, the GraphQL schema made a lot of sense. We could also reuse some work done in other projects, also considering GraphQL. But I think one of the really key benefits of GraphQL is the flexibility of designing queries. So if there are a lot of different trees, or if there are a lot of different branches of ESS that a specific service has to access, then in a typical REST world, it could lead to a lot of different REST API requests. But in a GraphQL world, it can really be, a service could really fetch data from different branches of the VSS data model in just one query, which makes it very flexible to work with. The GraphQL schema that is being exposed by the OEM cloud is currently using the schema generated in the Android Special Interest Group project. And on the other side, it's connected to the VSS database. So from there on, when the request comes in, then the GraphQL server can fetch the data, again using the REST interface or directly over SQL data from the VSS database, and then return it to the third-party service. In the currently kind of implementation, or it's a work in progress, we had first the kind of dummy data, but in this workshop I think we will be able to see also how data is actually being retrieved from the simulated data within the vehicle, so that we would have it end-to-end. So as for the third-party components, we have built a demo application written in Swift for iOS. So this demo application implements the GraphQL API that is exposed by the OEM cloud. It connects to that server, and then it reads the data. So we are both reading all the data we get from the server, but we're also kind of have been scoping it to specific signals that are used in this POC. What can be mentioned about the third-party application is that it's not just an application, but it's also using a library, a Swift library that consumes the VSS GraphQL API, and it also generates native objects or native classes in Swift that can be used. So it makes it very simple to use it, and it's more like an SDK for the VSS GraphQL API, and then also an application on top of this SQL API. One thing that can be mentioned, if we go back just one step here in this, is that we have the other two components, that the access management and the identity management. So of course, in any type of data access, there has to be some kind of authorization attached to it. And this framework also considering it that the data access, for instance, for personalized vehicle data, where you get the VIN, there is a driver consent done through OAuth 2. So this is very standardized. And then OpenID for authenticating the vehicle owner to actually give that authorization. But those implementations are not included yet in this POC, but of course it's a vital part of it. For the end-to-end demonstration, we will show in this workshop. During this summit, we will have a setup where we can demonstrate it, where the data is being generated in the vehicle, it's being fed to the state storage, it's being transmitted to the OEM cloud, and it's also made available to this demo application. So definitely check out that demo. It will not be part of the status report, but there's a separate video, or also a live demo coming up in the workshop. A few relevant topics that are worth mentioning when we speak about this, and one is the extended vehicle ISO 20078 is taken into consideration when we have been building this framework. And if you look at that resource management, so how the GraphQL API, in our case, the authorization, the authentication, all of that follows the kind of basic principles taken into account in the extended vehicle standardization. And that standard is in place for describing how technically telematics data is made available to third-party services. So this is a standard that is actively being adopted within the EU already, and it's also part of this framework. So it's definitely considering that same principle. The standard also says this, that it's about off-board data access, and also in this framework currently it's for off-board data access, as the data is being for third parties is being accessed from the OEM cloud, but the implementation from the vehicle to the cloud, that's of course also a part of this GENIVI or Cloud and Connected Services project. The second bullet point is the concept of a neutral server. So although I didn't show it in the status report, you could see the neutral server being part of the communication framework in the first slides. So we have no implementation of this yet in this project, but we have the concept is being considered. But for the POC, it's not part of the direct POC implementation, but the basic principle is the same, and that is that these neutral servers, they also multiply, or they are doing one integration with the OEM cloud, and then the neutral server itself has further third-party services that are being using it. So it's one, it adds kind of technical ease for these third parties to integrate vehicle data, because they can integrate with a neutral server and get access potentially to several OEM data. And it also, it's a kind of a business framework for the OEMs to multiply a data business when it comes to that. So that has also been included in the framework, and it's closely related with the extended vehicle in that sense that ATSEA, the organization, has also adopted this type of concept. It's also been adopted in practice in Europe. And we've done further investigations into different standards. There are several ones that are dealing with security. So how can secure connections being established between devices, and especially for in close proximity, for instance. So this is another kind of layer that can be considered on the communication framework in how data can be made available to third-party services, maybe not necessarily only off-board, but because this project looks at the holistic picture of the different ways that could be feasible to connect to vehicle data. And lastly, a few words about the CVII, or Common Vehicle Interface Initiative, which you've heard certainly a lot about in this summit already. To summarize in a nutshell, of course, it's a different project. CCS was started long before CVII, hopefully we can say it also that CCS has contributed to some of to some parts that are important to CVII, but also CVII scope is kind of bigger. It looks at standardization not only for the entire vehicle in the cloud and further on, and this will be more of a next project or a larger project kind of coming out of CCS, but not only from CCS but also from other initiatives from W3C mainly, and the plan is also to involve other organizations in getting into this type of work, and it is about driving standard data and service models across all these both the vehicle and the cloud in a nutshell. So definitely, if you think that this cloud and connected services looks interesting, definitely take part of the workshop that's also coming up today. And second is that the CVII is definitely very relevant if you think that CCS is relevant. Absolutely. With that, I would close this status report. Depending on when you're watching this status, we have a workshop coming up in the summit in just a few hours. And so hopefully you can join that, because we will go into each of these components again, but then look further into the implementation that we have been done. And we will have a lot of discussion about how the implementations can be done, what could be the impact. So this is really an excellent way of getting input and getting more information out of what we have done in the CCS project. So hope to see you there, and thank you very much for watching.